Hello, my dear students. Welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3 hybridization with one lone pair and one pi bond in the structure. And for this, I'm going to take an example of thionyl chloride. So today we are going to take an example thionyl chloride. The molecular formula for thionyl chloride is SOCl2, and I'm going to evaluate the hybridization of sulfur in SOCl2 to find out the structure with one lone pair and one pi bond having sp3 hybridization. So before doing that, let's make the Lewis structure of the thionyl chloride. So I'm writing that's my sulfur, that's my oxygen. Here I'm having chlorine and a chlorine. Now, what's the atomic number of sulfur? That's 16. So the configuration will be 2, 8, 6. That means sulfur is having 6 electrons in its valence shell. So I'm going to mark 6 electrons around the sulfur. That's first electron, second, third, fourth, fifth, and the sixth. Now let's talk about the oxygen atom. The atomic number of oxygen is 8. So the configuration will be 2, 6. That means oxygen is also having 6 electrons in its valence shell. So I'm going to mark 6 electrons around the oxygen atom. 1, 2, 3, 4, 5 and the 6. Now let's talk about the chlorine. The atomic number for chlorine is 17. So the configuration is 2, 8, 7. That means chlorine is having 7 electrons in the valence shell. So I'm going to mark 7 electrons around chlorine. I'm taking the first chlorine, the first electron, second, third, fourth, fifth, sixth, and the seventh. Here's first, second, third, fourth, fifth, sixth, and the seventh. Now, chlorine is going to make one bond with sulfur. Another chlorine is also going to make one bond with sulfur, and oxygen is going to make two bonds with sulfur. Now let's count the valence electron for the chlorine, the first chlorine after the formation of one bond with sulfur. That's first, second, third, fourth, fifth, sixth, seventh, and the eighth electron. That means first chlorine has attained the octet, that is 8 electrons, after forming one bond with sulfur. Now let's talk about this second chlorine. I'm going to count the valence electrons of second chlorine after the formation of one bond of chlorine with sulfur. So that's our first electron, the second, the third, the fourth, fifth, sixth, seventh, and the eighth. That means second chlorine has also attained the 8 electron in its valence shell after the formation of one bond with sulfur. Now let's count the number of valence electron for oxygen after the formation of two bonds with sulfur. So that's the first electron, the second electron, the third, the fourth, the fifth, the sixth, the seventh, and the eighth. So the oxygen has also attained the 8 electrons after the formation of two bonds with sulfur. Now let's count the number of valence electron of sulfur after the formation of two bonds with oxygen and one bond with one chlorine. So that's first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and the 10th. The sulfur has attained 10 electron in its valence shell after the formation of two bonds with oxygen and one bond with two chlorines. So here it's the case of expansion of octet. Why sulfur is able to expand its octet? Because of the availability of d orbital in its valence shell. So now let's talk about the hybridization of the sulfur. Why I'm taking sulfur? Because here in this case our central atom is sulfur in this case, because sulfur is forming maximum number of bonds. Now let's take the electronic configuration of the sulfur. Sulfur, the atomic number is 16. So the orbital configuration for sulfur will be 3s2, 3p4 along with 3d0. So let's make the orbital diagram for the sulfur. That's our 3s. As s is having only one orbital, that's why we have made only one orbital or the one box. That's the 3p subshell. P subshell is having 3 orbitals, that's why we have made 3 boxes, and they are of equal energies and they are also called degenerate orbitals. Now let's talk about the 3d subshell. The d subshell is having 5 degenerate orbitals, that is orbitals with equal energies. So the 5 orbitals of 3d are having equal energies. Then the 3 orbitals of 3p are also having equal energies. So we are having degenerate orbitals, the 3 degenerate orbitals in 3p and the 5 degenerate orbitals in 3d. Now let's fill the electron. The 3s is having, the 3s is having 2 electrons. The first electron with a spin of plus 1 by 2, the second electron with a spin of minus 1 by 2. The 3p is having 4 electrons, so we have to fill the 4 electrons according to the Hund's rule, and states that firstly all the degenerate orbitals will get 1 electron each. After that pairing will start. So that's our first electron, the second electron, the third electron and the fourth electron. And that's our ground state. This is our ground state. Now let's come to the Lewis structure. In the Lewis structure we can easily see that there is a formation of 4 bonds. I am writing sulfur is forming total of 4 bonds. Total of 4 bonds. And in this case oxygen is forming 2 bonds. Whenever an element forms a double bond, then out of that 2 bonds, the one bond is sigma and the another bond is pi. And whenever an element forms a single bond, that's always the sigma bonds. That means here we are having total of 3 sigma bonds and 1 pi bond. So firstly, there is a formation of 4 bonds. That means we need 4 electrons in 4 different atomic orbitals. Only then sulfur will be able to form the total of 4 bonds. So here what's gonna happen, there's the ground state. Now in this case the 1 electron from the 3p orbital will get excited to the orbital of the 3d subshell. So that means I'm going to make the excited state now. That's our 3s. That's our 3p. And that's our 3d. And here the 3s is having 2 electrons. The 3p is now having 3 electrons, as one of its electron has excited to the 3d subshell or the 3d orbital. We got the 1 electron over here. So firstly that's called the excited state. This is our excited state, and in the excited state we are having 4 electrons in 4 different atomic orbitals, which makes sulfur eligible to form the 4 covalent bonds. Now let's talk about, out of that 4 covalent bonds, how many are the sigma bonds. So we are having total of 3 sigma bonds. So at this step hybridization will take place, and in the hybridization we will consider only that atomic orbitals which will form the sigma bonds. So here we are having total of 3 sigma bonds. That means in the hybridization process, one of the s orbital and 3 p orbitals will intermix for the hybridization. So here 1 s orbital and 3 p orbitals will intermix. they will intermix. The intermixing of atomic orbitals, we know that what's it called? That's called hybridization. And here, why we have taken the 1s and the 3p orbitals? Because in 3p orbitals we are having 3 electrons, and in the structure we were having the 3 sigma bonds. That's why we have to consider the 3 orbitals having 1 electron each for the sigma bond formation. We don't have to consider the orbital of the 3d subshell because it will be used in making the pi bond. And hybridization, or we can say the hybrid orbitals only form these sigma bonds. Let me write this thing. Hybrid orbitals only forms sigma bonds. So here we are having total of 3 sigma bonds. That's why we have taken the 3 orbitals of 3p subshell having 1 electron each for the formation of 3 sigma bonds, and the 2 electrons of 3s will be considered as the lone pair. So here we have mixed 1s and 3p orbitals, so there a total of 4 orbitals are intermixing. So we will get the equal number of new hybrid orbitals. That means we will get the 4 hybrid orbitals of the equal energies. So that's the 4 hybrid orbitals of equal energies, or we can say the degenerate hybrid orbitals, and the name of each hybrid orbital will be sp3 because it has been formed by mixing of 1s and 3p orbitals. Second one is also sp3, the third one is also sp3 hybrid orbital, and fourth one is also sp3 hybrid orbitals. So in these hybrid orbitals we have to fill total of 5 electrons because 2 electrons were in 3s and the 3 electrons were in 3p, so there were total of 5 electrons. So we are going to fill that 5 electrons according to the Hund's rule. So that's the first electron, second, third, fourth, and the fifth. After that we are also having 3d alongside, so I'm making that 3d also. That's the 3d subshell which is having 1 electron. Now what next going to happen? Let's talk about the chlorine and the oxygen now. I'm writing chlorine over here. What's the electronic configuration of chlorine? Its atomic number is 17, so configuration will be 3s2 3p 5. So let's make 3p subshell with 3 orbitals. Here it's having the 5 electrons in 3p, so that's first, second, third, fourth, and the fifth electron. So here one of the 3p orbital is having 1 electron which will have the head-on overlap with the sp3 hybrid orbital of the sulfur. So I'm writing over here, first of all, this is the 3p of first chlorine, and it's having 5 electrons, 1, 2, 3, 4, 5. Now here in this case one of the 3p orbital is having only 1 electron which will have the head-on overlap with the one of the sp3 hybrid orbital of sulfur to form the sigma bond, and that sigma bond will be sigma sp3p because it has been formed by head-on overlap of sp3 hybrid orbital of sulfur with the p orbital of the chlorine. So that's why this sigma bond is named as sigma sp3p. Now let's talk about the second chlorine. That's the 3p subshell of second chlorine. I'm writing 3p of second chlorine. Now here also the 3p will have the 5 electrons. That's the first, second, third, fourth, and the fifth. Here again you can again notice that one of the 3p orbital is having 1 electron, so it will have the head-on overlap with the sp3 hybrid orbital of the sulfur forming the sigma bond, and that sigma bond will be again named as sigma sp3p because it has been found by the head-on overlap of sp3 hybrid orbital of sulfur with the p orbital of the chlorine. Now after that, now let's talk about oxygen. Now let's talk about oxygen. What's the oxygen atomic number of oxygen? It's 8. So its uh, valence electronic configuration in terms of orbital will be 2s2 2p 4. So let's make the 2p subshell of oxygen. We are having 3 orbitals in 2p. So that's the 2p of oxygen. It's having 4 electrons. So that's the first, second, third, and the fourth. So let's make it over here. That's first, second, third, and we got the 3 orbitals, and that's the 2p of oxygen atom. Sorry. So we are having 4 electrons in the 2p of oxygen. That's the first, second, third, and that's the fourth electron. Now here we are having 2 orbitals of oxygen which are having 1 electron each, and out of that one orbital will have the head-on overlap with the sp3 hybrid orbital of the sulfur forming the sigma bond, and again that sigma bond will be named as sigma sp3p because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of sulfur with the p orbital of the oxygen. Now on the another hand, the another orbital of 2p having 1 electron will have the side overlap or the lateral overlap with the 3d orbital of sulfur forming the pi bond. So this pi bond will be pi 2p 3d because this pi bond has been formed by this pi bond has been formed by the lateral or the sidewise overlap of 2p orbital of oxygen with the 3d orbital of the sulfur, and this pi bond will be also named as p pi d pi bond because this pi bond has been formed by lateral overlap of p orbital of oxygen and the d orbital of sulfur. That's why it is named as p pi d pi bond. Now here we are left with one thing. In this case, we are in case of one of the sp3 hybrid orbitals, we are having 2 electrons, and these 2 electrons will be counted as the lone pair of electrons. Lone pair of electrons in one of the sp3 hybrid orbital of the sulfur. Now let's talk about the geometry. Which hybridization we have got over here? We got the sp3 hybridization. What's the standard structure for sp3 hybridization? That's tetrahedral. So we are having sulfur over here. So here we are having one lone pair at one of the tetrahedral position. The double bond O on the another tetrahedral position, the chlorine over here and the chlorine over here. Here let's mark the types of bond over here. This sigma bond is the bond between sulfur and chlorine is sigma sp3p because it has been formed by head-on overlap of sp3 hybrid orbital of sulfur with p orbital of chlorine. Same way another bond is also sigma sp3p, and the sigma bond between sulfur and oxygen is also sigma sp3p, and lastly the pi bond over here formed is p pi d pi bond. Now, here lone pair is present, so we will not call this geometry to be tetrahedral. This will be called as trigonal pyramidal. This geometry will be called as trigonal pyramidal. Now, at last, let's talk about the energy points. Here, two types of energy are consumed. The one is energy consumed during the promotion of electron. So, I am writing here consumption of energy during promotion of electron or the excitation of electron from 3p to 3d. And the another energy consumed is during the intermixing of atomic orbitals, or we can say the hybridization energy. So here is also the consumption of energy, or we can say consumption of hybridization energy. After that, when there is a formation of 3 sigma bonds and even pi bond, the energy is released. I am writing the energy is released during formation of 3 new sigma bonds and 1 pi bond, which compensates the promotional energy and hybridization energy. And hybridization energy. That's why the formation of thionyl chloride or SOCl2 is practically feasible or possible in terms of energies. So that's all for today. I hope you all understood the hybridization of SOCl2, that's sp3, which is having one lone pair and one pi bond in the main structure. So that's all for today. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.